Okay, in this video I'm going to talk about the Newton-Gauss line. So let's say that we have a quadrilateral. So a quadrilateral like that, something like that, and we consider the midpoints of two of its sides. So the opposite sides, two of its opposite sides, like that. So these are midpoints. And then we consider another midpoint. So first we take the intersection of the diagonals, and we take the intersection of the other two opposite sides, the extensions of two other opposite sides. So like this, and we take this segment connecting the intersection of the diagonals and the intersection of the extensions of the two opposite sides, and we take the midpoint of this segment. So these are equal. And the theorem is that these 3 points, these 3 midpoints, lie on the same line, so they are collinear, and this line is called the Newton-Gauss line. So let's denote the points. So A, B, C, D. P, Q, and the midpoints M, N, and L. Yeah, so let me actually, okay, so yeah, and so theorem is that M, N, L, these 3 points lie on a line, like let's write lie on a single line, which is called the Newton-Gauss line. Okay, so let's prove this. So we introduce several more midpoints. So in particular, we introduce the midpoints of this triangle. So let me highlight this triangle. So BAP, and there are other ways to make the same argument. Like we can pick another triangle, but it doesn't matter. So we so we select the midpoints of this triangle. So, and let me denote them by X, y, and z. So these are the midpoints. So this segment is equal to this segment. This segment is equal to this segment, and this segment is equal to this segment. Like, I don't know how to denote them. Yeah, so let's denote it like this. Yeah, so now because these are like a bunch of midpoints, like we notice that if we extend this, so this small triangle, right? So if we extend these lines, it's easy to see that it would fall exactly at M. So xz would pass through exactly M, like y would pass through L, and zy would pass through N. And so why is that? Well, it's because, like, so let's say xy, right? So xy is connecting the midpoints in this blue triangle, so it is parallel to BA. So and so xy is parallel to BA, but in the large triangle, in the triangle BPQ, we have like also the midpoints x and L. So XL is also parallel to BQ. BQ and BA is the same line, right? So this line. So therefore, it implies that XL, X, Y, and L are collinear. Well, like we can just see that like they all lie, like if we have a homothety with center P that scales everything, like makes everything twice smaller, then B maps to X, A maps to Y, and Q maps to L, right? So like B, A, and Q lie on the same line, therefore the mappings, the points where it's mapped, X, Y, and L would also lie at the same line. So like, so we can make an argument with homothety or with similar triangles or with parallel lines, like it doesn't matter, like it's like it's easy to see that these points are collinear. Similarly, Z, X, and M are also collinear because this line is parallel to AC, like right. ZX is parallel to AC, and the third line, so ZY is parallel to BP, and it passes through the midpoint of AD as well. So yeah, so now so let's write the Menelaus theorem for this blue triangle and the line QC. So we write the Menelaus theorem. Menelaus theorem for the triangle ABP and the line QC. So this line, let me select it in green. So for the blue triangle and the green line. So the Menelaus theorem is that so we start with some vertex. Let's say we start with B and we go counterclockwise. So BQ over QA, right? Q is the intersection point of the green line with the side BA of this, well, the extension of the side BA of this triangle. So multiplied by, so this is equal to -1. So -1 is equal to this product. Then AC, C is the intersection point of this line with this side. So AC over CP. So AC over CP. And then PD over DB. Right, now let's rewrite now this. So yeah, so it was written incorrectly. So the Menelaus theorem for the triangle ABP and line QC. Okay, so so now we see that BQ, so let's say this this ratio BQ over QA, so BQ over QA. So we simply write for similar triangles, so like again with the homothety with center P that scales everything twice smaller, right? So BQ is mapped to XL, so XL over LY over LY. Or we can simply notice the similar triangles. So the like this triangle BXL is similar to PXL is similar to PBQ. So XL with the ratio 1/2, right? So XL is basically, so this like BQ, so BQ is equal to 2XL and QA is equal to 2LY. They're all twice smaller. So LY is twice smaller than QA. So that's why the ratio is the same. So and the similar for the other two ratios. So let me remove this. So AC over CP. So AC over CP. So like now we consider the homothety with center B. So it scales everything twice smaller. So now AC is mapped to ZM. So the ZM over MX. And the third ratio, PD over DB. So PD over DB. So now we scale everything with center A, twice smaller. So PD is mapped to YN over NZ. Yeah. And so this becomes, so we have the product of these three ratios. Now we notice what is this product. So XL So XL over LY. So now, basically now we consider the triangle. So let me select it with yellow. This small triangle and these 3 points, right? The 3 points that we need to prove that they lie on the same line. The 3 midpoints M and L. So like it's easy to see that this is simply the product of this ratio that we get is simply the Menelaus theorem for this triangle and these 3 points. So XL over LY multiplied by YN. So now we need to change places of these 2 ratios, right? So let's write this. So XL over LY multiplied by YN over NZ multiplied by ZM over MX. So we simply exchanged the places of the last 2 ratios. So now we have exactly the Menelaus theorem. So XL over LY multiplied by YN over NZ multiplied by ZM over MX. So the product of these 2 ratios is equal to -1. So this is what we proved. So by the Menelaus theorem, so it follows that by the Menelaus theorem for the triangle XYZ, for the triangle XYZ, and the line, not the line, but the points, and the points, because it's the converse statement, right, in the Menelaus theorem. So it's, and the points L and M, we conclude, so by this Menelaus theorem we conclude that these 3 points are collinear. We conclude that L and M are collinear, which is exactly what we needed to prove. L and M lie on a single line. This is exactly what we get. So this concludes the proof.